Welcome back. This is Coach Dorf. We're looking at another problem from section 4.7 on optimization problems. In this problem, you have a river that is 1 kilometer wide. So we have that is 1 kilometer. And on one side of the river, you have a refinery. Put that right there as that box. And on the other side here, at a distance of 2 kilometers, you have some tanks here, storage tanks. And now you want to build a pipeline that will go from the refinery to the storage tank. Now it costs more to build the tank under the water in the river than it does on the land. But at some point you have to go across the river. So the question is, where do I put a point P that's on the same side as the refinery so that the cost will be least, it will minimize the cost in building the pipeline. So there's my point P. We're going to call this distance X. And so then we know that the distance from the refinery to P is going to be 2 minus X. All right. And if I look at this, I notice that from point P, and I have the distance X here. Then if I go down, I have across the river, there's 1 kilometer. This hypotenuse here, draw in there, that's going to be the length of the pipe under the river. And the length of the pipe on land is equal to this distance from the refinery to P. So it's going to be that distance there. All right. So let's look at these numbers. So when I have the triangle here, I've got X and 1, I can use Pythagorean theorem to figure out that this length here is equal to the square root of X squared plus 1. And as we showed earlier, this length here is 2 minus X, since the total distance from the refinery to perpendicular from the storage tanks is 2, and from P to that point is X, so that must be 2 minus X. So the cost of the laying the pipe is going to be the cost it takes to lay it on the land. So that's going to be $300,000 times length of pipe on the land plus $500,000 times length of pipe the pipe under the river. So what are those numbers? So I'm going to write like just 300 here, 300,000. The length of that pipe we said was 2 minus X plus 500,000 times the square root of X squared plus 1. Now, I can go ahead and drop the 100,000. It's not going to affect it. In fact, so in other words, you're thinking, I'm just going to factor out 100,000. So we're going to let my function actually just be 3 times 2 minus X plus 5 times square root of X squared plus 1. I've divided out by 100,000, so the numbers are easier to work with. All right, we want to minimize this, and so we'll use second derivative test. So to do that, we first find critical points, critical numbers, and that's where the derivative equals 0. So I'm going to look at the derivative. The first part, I'm going to take that derivative of 3 times parentheses 2 minus X. I'm going to get a minus 3 in there. Now when I take the derivative of 5 times the square root of X squared plus 1, I'm going to end up with 5x over square root of X squared plus 1. You may have to work that out, but you can do that. And that all equals 0. So then I've got 5x over square root of X squared plus 1 equals 3. And if I cross multiply, that's going to give me then 5x equals 3 square root of X squared plus 1. But now I'm going to square both sides, so I get 25x squared equals 9 times x squared plus 1, which is 9x squared plus 9. So simple, bringing the x squares to the one side, I get 16x squared equals 9, or x squared equals 9/16. And taking the square root of both sides, I get plus or minus 3/4. But since we're dealing with distances, x is the distance, we're only concerned with only have x equals positive 3/4, since x is a distance. Now I need to, that's my critical number there. Now I need to take the second derivative. So let's look at the second derivative here. So looking at what I have there, remembering, of course, up here, here is my first derivative. So my second derivative, derivative of -3 is 0. The derivative of 5x over the square root of x squared plus 1, I'm going to use the quotient rule. So that says the derivative, says the bottom times the derivative of the top, 5, minus the top times the derivative of the bottom. The derivative of that is going to be x over square root of x squared plus 1, all over the denominator squared. Now I'm going to factor out a 5 over the square root of x squared plus 1, because that'll allow me to make things simpler in the numerator. And when I do that, I'm left with an x squared plus 1 minus an x squared. And that's all over the denominator, which I can rewrite as x squared plus 1. So simplifying that, I see that I get 5 over square root of x squared plus 1 times x squared plus 1, which of course I could rewrite that in the denominator as just x squared plus 1 to the 3/2, but I just wrote it like that. Now, is this going to be positive or negative? Well, this is always going to be positive. And so when I have a positive second derivative, that means I have concave down, which means I then have a minimum. So x equals 3/4 is a minimum, and that's the answer to our problem. So when going back to the original situation here with the river, and here's the refinery, and here are the tanks. This distance was 1 kilometer, and this distance was 2 kilometers. You want to make the point here. So this is 3/4 of a kilometer, and this length here then is going to be 5/4 a kilometer. And that will minimize the cost of building the pipe. Hope that helps.